Hello, everyone. I'm Prashant. Today in this talk, I will tell you about our work on the filter design, which overcomes the decade-old trade-offs in terms of the time and the space usage of the filters. This is a joint work with Alex Conway, Joe Dury, and Martin Fudge-Colton from Rutgers, Michael Bennett from Stony Brook, and Rob Johnson from VMware Research. So let's start by talking about the filters. A filter is an approximate representation of a set. For example, on the left-hand side, we have items from a universe containing A, C, B, and D, and a set, which is a part of the universe containing item A and C. A filter representation can answer the membership queries of the items from the set, and it will always return true for items that are present in the set. However, occasionally, it might still return true for items that are not part of the set. For example, in this case, item D. And these items are false positives. Formally speaking, if Q is not part of the set, then with probability smaller than equal to epsilon, filters might return true. And these items are called false positives. Important point to note here is that the filters always have one-sided errors. From that I mean, they will never be a false negative, they can only be false positives. So why do we care about the filter data structures? The filter data structures use much less space compared to an exact data structure like a dictionary. On the left-hand side, we have the space usage of the filter, which is dependent on the false positive rate of the filter, for example, epsilon. On the right-hand side, we have the space usage of a dictionary data structure, which is dependent on the size of the universe. A common rule of thumb is if we, for most practical purposes, we configure the filter data structures to have 1 to 2% false positive rate. And in those cases, a filter data structure uses 1 byte per item compared to a dictionary data structure that can take anywhere between 8 to 16 bytes per item, depending on the size of the keys. Filters are ubiquitous across computer science. They are used in various different subfields, for example, in databases, in storage systems, in networking, in streaming applications, and in computational biology. Now let's talk about the design objectives of a filter data structure. So we want to design a filter data structure that has a very small, that use small space or close to optimal space usage of a filter data structure. We want to perform operations like insert, deletes, and queries in constant time or the constant CPU cost. Moreover, we also want to make sure that the locality of these operations is very good, because most of the time the performance of operations like inserts, deletes, and queries in the filter data structure is bottlenecked by the cache locality or the number of cache misses that happens during these operations. And therefore, it is very important to have a good data locality while performing these operations in order to guarantee a high throughput. Now let's talk about existing filter data structures. The first filter data structure was introduced 5 decades back, called the Bloom filter. The Bloom filter data structure is one of the highly used data structure across computer science. However, over the years, there have been many different types of data structures that try to overcome one or the other drawback of the Bloom filter data structure. Specifically, talking about the state of the art in practical dynamic filters, there are the Quotient filters and there is the Cuckoo filter. Both of these filters support deletes and also support higher throughput operations in terms of inserts and queries compared to a Bloom filter data structure. The Quotient filters moreover support other features like enumeration, merging, and resizing over the Bloom filter data structures. There are other types of the filter data structures which are static in nature and are based on some technique called perfect hashing or linear algebra. For example, the XOR filter. Now, even though there has been decades of research in the filter data structures, the current state-of-the-art filter data structures still suffer from a drawback. For example, in this plot we are showing the x-axis is the load factor. What that means is how full is your data structure, and the y-axis is the throughput, or specifically insertion throughput, so higher is better. If you can see, for all of the 3 state-of-the-art filter data structures, as they become full, the performance or the throughput of the insert operation drops considerably. The main reason behind the performance drop is that once the data structure becomes the fuller, they have to pay a high overhead cost of collision like resolution in the filters. What that means is that now applications have this implicit trade-off in terms of the space and the speed. However, there are many update-intensive applications. What they care about is the performance of the filter data structures at high load factors, because they always maintain the filter close to full and they do update operations like inserts and delete continuously on the filters. So therefore, for these applications, these existing state-of-the-art filters, they have this implicit trade-off in terms of space and speed, which hurts the performance of the application. Now, in this talk, I will tell you how to build a new type of data structure, or the filter data structure called as the vector quotient filter, which supports constantly high throughput from empty to full. So the insertion throughput or the insertion performance of the vector quotient filter data structure is constant regardless of how full the data structure is. What this means is that now applications which are update intensive can maintain the data structure at a very high load factor, for example, 90 to 95% full, and they keep on doing inserts and delete operations without any loss in the throughput of the insert operation or the delete operation. So before we talk about how to design the vector quotient filter data structure, first let's understand why or what is the main reason behind the slowdown in the quotient filter and the cuckoo filter data structure. So the quotient filter data structure is based on Robinhood hashing, which is a variant of linear probing. In the Robinhood hashing, the quotient filter makes sure that all the items that have hashed in the same location, the fingerprints of all those items are stored together in the form of a run. For example, in this array on the top, we have 3 different runs, which are in the color purple, blue, and yellow. To identify the home location of every fingerprint, the quotient filter uses 2 extra bits per slot. To insert any item, we first determine the home location or the home run of that item. And in order to make sure that all the fingerprints that belong to the same run are stored together, the quotient filter requires to shift existing items down by 1 slot to make space for the new incoming item. In this case, to store the item X, the existing fingerprints from F1 to F6 are shifted by 1 slot to the right, and the new fingerprint FX is stored to make sure that all the fingerprints in purple are stored together. This shifting operation becomes the number of items that are shifted during any insert operation becomes larger and larger as the data structure becomes full. And this is the main reason behind the slowness of the insertion throughput when the data structure becomes full. Now let's talk about the performance of the quotient filter data structure. So in terms of the space usage, the quotient filter data structure is close to optimal, but it has an overhead of 2.125 bits per item in the data structure. In terms of the CPU cost, the insert or the query operations or delete operations can be performed in constant time in expectation. And there's a proof in the paper that shows that we can perform these operations in log n time with high probability. In terms of the locality of operations, for do any operation, we have to do a single probe to find out the run for every new incoming item. And then in cases when there is a long run, then we have to do like a sequential scan. So 1 probe plus a sequential scan. So there's a very good data locality for all different types of operations like insert, deletes, and queries in the quotient filter data structure. Now let's talk about the cuckoo filter data structure. Instead of one giant array, as in the quotient filter data structure, the cuckoo filter data structure has a block architecture in which there are multiple blocks, and each block can contain up to 4 items, where 4 is a very small constant. To insert any item, we hash the item twice, like H0x and H1x, and we find the empty block, and if one of those blocks is empty, we insert the item, and we are done. However, if both the blocks are full, then we have to do some kind of a kicking. For example, in this case, to insert item X, where both the blocks are full, we have to kick an existing item to its alternate location. For example, in this case, F8. However, since the alternate location is also full, we have to kick again, this existing item like F12 to its alternate block, and keep on doing that until we find an empty location or empty slot. Important point to note here is that since the fingerprints are lossy, which are stored in the data structure, In order to compute the alternate block of existing fingerprints, you have to make sure that these two hash functions are dependent on each other. They use an XOR operations to compute these alternate locations. Now, as the data structure, the quotient, sorry, as the cuckoo filter data structure becomes the fuller, the number of random kicking that has to be done for any insert operation increases. And that is the main reason behind the slowdown in the insert performance of the cuckoo filter data structure. Now, in the worst case, the number of kicking can be up to 500 before they call the data structure to be full. So the random probing and the kicking around during an insert operation is the main reason behind the slowness in the cuckoo filter. In terms of the performance, the cuckoo filter also has a very space efficient architecture in which they're close to optimal, but have a 3-bit of overhead per item in the data structure. In terms of the CPU cost, for doing an insert operation, the number of probes or random probes can go up to 500 in the worst case. But during a query operation, they do exactly 2 probes to find the fingerprint in one of the 2 locations. In terms of data locality, again, for insert operations, the data locality is pretty bad because they have to do these random probes across the whole data structure. But in terms of the query operation, the data locality is pretty good because they have to do exactly 2 probes to do any query operation. Now, we have learned the main reasons behind the slowdown in the insertion performance of the quotient filter and the cuckoo filter data structures. Now let's see how we design the vector quotient filter to overcome both of these issues. So the vector quotient filter has a block design similar to the cuckoo filter data structure. However, unlike the cuckoo filter data structure, the size of each block is not a small constant. The size of each block in the vector quotient filter is bigger. Specifically, it is omega log n, which in most practical cases is close to 64. So now we are supporting a block design, but each block is much bigger in size. Now, to maintain the architecture or to maintain the items inside each of these blocks, we use some kind of structure because to do these operations, inserts, deletes, and queries inside each block, we have to maintain some structure to do them efficiently. Specifically, each of these blocks is a mini quotient filter, wherein we have some space for the metadata, which is exactly 2 bits per item in the block. And then we have the 64 items in that block. So each of these blocks is a mini quotient filter data structure. Important point to note here is that given that the quotient filter, the reason behind their slowness was the fact that we have to do a lot of like the shifting during any insert operation. But now in the mini quotient filters, the size of the quotient filter is very small, which is only like say like the 64 items that can in most cases to fit inside 1 or 2 cache lines. And therefore the slowness behind the main reason behind the slowness of the quotient filter is not there anymore because we don't have to do unbounded amount of shifting. We have to do these localized operations, which are very small. To do any insert operation in the vector quotient filter, we do the similar operation like taking the item and hashing it twice, finding 2 locations and inserting the item in the emptier block. But unlike the cuckoo filter, we don't have to do any kicking. So what we do is that we hash the items twice and we find the 2 locations and we insert the item in one of those in the emptier block, but we don't have to do any kicking. What that also means is that since we don't have to do any kicking, the 2 hash functions can be independent of each other if we have an insert only workload. However, as we explained in the paper, if we have to support deletes as well, then we have to make sure that the 2 hash functions are dependent on each other using the XOR operation. Now, there's a result from walking which shows that if the size of each of these blocks is big enough, which is omega log n in size, then we can prove that the variance in the block occupancy of these blocks will be lower order term. What that means is that we can bring the data structure to a very high load factor without filling up anyone's block. What that actually means is that by using this trick of using power of 2 choice hashing, where the size of each block is high enough or big enough, we can reach a very high load factor without making any of the blocks to be full. Another aspect of using exactly 2 blocks and not having to do any type of kicking is that we can easily implement a concurrent version of the data structure where we can support insertion using multiple threads. Now, let's talk about how we do these operations or like insert, delete, or query operations inside each of these mini quotient filters. Given the fact that these mini quotient filters are small and they can fit inside one or maybe at most two cache lines, we can do these operations very, very efficiently using clever instruction sets. Specifically in the paper, we show that we can operate or do these metadata operations in the mini quotient filters using Intel's AVX2 line of instruction set. Those were introduced close to a decade back now. And to do the shifting operation, we have two types of implementations. In the first implementation, we actually exploit the newer, like the set of operations from Intel, which are the vector instructions, AVX512. And we can show that we can do these like the shifting operations in a constant time by using very few number of instructions. If the machine doesn't have the support for AVX512, then we also have an implementation where we show how we can use traditional AVX2 instructions to do these operations and still be very fast and in almost constant time to do these operations inside the mini quotient filters. And according to this, the vector model of computations, when we have these blocks which are of size omega log n, which in most cases can fit in very small number of cache lines, we can do these operations or the insert operations or the delete operation or the query operation inside the mini quotient filters in constant time. Specifically, we show how we use AVX512 instructions to do these in the paper. And so now let's talk about the performance of the vector quotient filter data structure. So we see in terms of the space usage, the vector quotient filter has a similar space usage as the cuckoo filter, wherein the overhead, the space overhead per item is very small, which is 2.91 bits per item. In terms of the CPU cost for doing any operation, insert, delete, or query is constant time. It's exactly 2 probes per item. And in terms of data locality, we have very good data locality for every operation, for be it inserts, be it deletes, or be it queries. So we do exactly 2 probes for any operation in the vector quotient filter. And these theoretical performance like results translate into actual performance empirically. So here we show that when we use the vector quotient filter, we can support constantly high throughput irrespective of the load factor for the insert operation. In the paper, we talk about an optimization in the vector quotient filter, which achieves us even higher throughput for load factors up to like 75%. And then it matches, flattens the curve and becomes the same as the vector quotient filter without any optimization. In terms of the query operation, the vector quotient filter needs to do 2 probes, which is exactly the same as in the cuckoo filter data structure. However, in the cuckoo filter data structure, the size of each block is much smaller and the overhead of performing a query in these blocks is small compared to the vector quotient filter. Therefore, as you can see, in terms of the query, the cuckoo filter has slightly higher performance, a constant time high performance compared to the vector quotient filter data structure. We also implemented a multi-threaded version of the vector quotient filter, which supports insert operations or query operations in the presence of multiple threads. And we show that given the fact that we don't have to do any kicking, for any operation, we just have to do 2 probes exactly. This helps us to implement the multi-threaded version very, very efficiently. And with increasing number of threads, the throughput of insertion scales almost linearly. So finally, to conclude my talk, I want to say that the vector quotient filter outperforms current state-of-the-art filter data structures in terms of the throughput for insert operations or the delete operations or the query operations. We also show that by using the combination of techniques like the power of 2-choice hashing and the Robinhood hashing, and using this new vector model of instructions, we can actually overcome this decades-old time and space trade-off in the filter design. Thank you so much, and I will take questions now.